to be? Software engineer. Well, all of computers and all of technologies from math. That's why. All technology, all science is based off of math. That's why. If you don't understand math, then you can't really understand the science or the technology. Because the math is how it even works, right? Math is why it works.
Yeah, but I don't think we use a lot of it, like a lot of math in coding.
Correct. You don't use like a lot of math in coding, but math helps you learn about how to think about solving problems.
Yeah.
Right? That is where it does get used in coding. The skill of problem solving is what gets used in coding. Okay. So we're moving on to chapter 5. Let's verify identities. Let's do 1 minus tangent t quantity squared. We'll just say x is equal to secant squared x plus 2 tangent negative x. Okay, prove this. So we can start with the right-hand side. We'll rewrite it. We notice that this decomposes to 1 over cosine squared x plus 2 times sine of negative x over cosine of negative x. We remember sine is an odd function. This implies that the sine of negative x is equal to negative sine of x. And remember that cosine is even, which implies that cosine of negative x is equal to just cosine of x. Okay, so that means here we can rewrite this as 1 over cosine squared x minus 2 sine of x over cosine of x. Multiplying top and bottom here by cosine x, establish a common denominator, we get that this equals 1 minus 2 sine x cosine x, everything divided by cosine squared x. Okay, so how does this end up equaling 1 minus tangent quantity squared? Well, we can start to think about what is 1 minus tangent quantity squared. Notice that's 1 minus 2 tangent x plus tangent squared x. So we want this to equal that. How are we doing in our journey to get there? Say what? They could, if that's the direction you want to go, they could, but that's just going backwards over here to here. Now I will say that this piece right here does equal a -2 tangent x. And that is a piece that we want. And notice that we have 1 over cosine squared x. This equals a what? Secant squared x. Do you guys remember the identity for secant is tangent squared x plus 1 is equal to secant squared x? We've proven that identity before. So notice that if this is a -2 tangent x and we have a secant x, we can replace that with all of this. Which means this becomes a tangent squared x plus 1 minus a 2 tangent of x. Oh, but that's exactly what we were trying to show. So we're done. Does that make sense? Our task was to prove this thing, that 1 minus tangent x quantity squared is equal to secant squared x plus 2 tangent of -x. So we started with secant squared x plus 2 tangent of -x. And we got this, which then decomposed to this by definition of tangent, which then decomposed to this by the odd and even properties of sine and cosine. And then we're able to establish that this piece is the -2 tangent x of what we're trying to show. And then that the secant squared x gives us this 1 and that tangent squared part. Let's do some more practice problems. We're 5.1 for those of you who don't know. It's 5.1. I know you're wondering about the test, but not everybody's taking it, so we're not going to review it. Nope, haven't graded it. Let's do another one. Let's do sine squared x tangent squared x. So this equals tangent squared x minus sine squared x. We want to prove this. So, guys, proving is like this. How do we prove? 12 equals 3 times 4. How do we prove this thing? Well, we start with 3 times 4. Show that this equals 3 added to itself 4 times, or that is 4 added to itself 3 times. But in either case, we show that that equals 12. So to prove 12 equals 3 times 4, you start with 3 times 4, show that that equals 12. So to prove this, we got to start with one side of the equation, manipulate it to show that it equals the other side of the equation. All right.
So would we turn these hands into like secant, cosine?
Say what?
Would you turn the hands into sine and cosine, like over each other?
Yeah, why not? Let's start off. Which side of the equation do you want to start off with?
The right side.
Sure, let's start off with the right side. So I'll reproduce it. Now we have to move to the left side. And you said replace tangent with its definition. Sine squared x over cosine squared x. Right?
Yeah.
It should say sine squared x. Now we notice that we don't have a common denominator. So we have to multiply top and bottom by fancy number 1 to establish a common denominator. So then we get sine squared x minus sine squared x cosine squared x. Everything divided by cosine squared x. Recall, we started here. We want to end here. We want to end at sine squared x multiplied times tangent squared x. What can we do from this point here? What can we do from that point? Oh, what was that? Factor out a sine squared out of the numerator? Yes, excellent suggestion, favorite student of mine. My favorite student is an imaginary student, apparently. That way, none of you guys get left out. That you're not the favorite student. My favorite student just said, factor out a sine from the numerator, right? A sine squared. Does that make sense? Notice, guys, that this has a sine squared term. This has a sine squared term. So I can pull it out. This becomes a 1. And this becomes what is remaining, that cosine squared. You guys see that? Why would I do that? Well, I want to eventually have a tangent squared times a sine squared. I noticed that this can get me that tangent squared part. All that remains is to convert that 1 minus cosine squared part into a sine squared. Well, how are we going to do that? Oh, what was that? My favorite student is at it again. Why not utilize the Pythagorean identity? And I'll highlight the Pythagorean identity in yellow and in a box. That sine squared x plus cosine squared x is equal to 1. Oh, but favorite student of mine, that isn't readily useful. We have 1 minus cosine squared x. That's not here. So you're starting to not become my favorite student. But maybe we could do something to that, and maybe one of you guys could become a new favorite student. From both sides? Okay, Marcus is on his way to becoming the new favorite student. So now you're suggesting that this can be replaced with all of that, right? Ah. Oh. Now what? No.
Oh.
We're done.
Does it have to be in that order?
What?
Does it have to be like in that certain order?
What do you mean does it have to be in that certain order?
Because over there is sine times tangent, right? And now tangent.
Ah, that is your question. Well, I'm going to answer your question with a question of my own. What is 3 times 4? What is 4 times 3? Nope. No, because the real numbers form a commutative ring with unity. But this is not true inside the intense gravitational curvature of a black hole. So at least for our simple-minded mathematics, we'll assume that 3 times 4 is equal to 4 times 3. This is not true inside of a black hole. Well, it might be. Who knows? Nobody knows what happens in there. Not yet. Ah! So are we done?
Yeah.
Yeah, we're done. Of course. Don't let my incredulous sounding voice fool you. I mean, that's the real test, right? We're done. You have to know, no, yeah, we're done, even though you're making it sound like we're not. Do you guys remember why that equation was true? You guys remember why that was even true? Let me remind you why that's true. Here's a unit circle. So the hypotenuse is a 1. You bring it down, here's the x and here's the y. You use the Pythagorean theorem, x squared plus y squared is equal to 1 squared. But notice that that's the same thing as cosine squared x plus sine squared x is equal to 1. Because the x and the y parameterize cosine and sine respectively. Notice that the cosine of theta is adjacent, which is x over hypotenuse, which is 1, which is just x. Notice that the sine of theta is opposite over hypotenuse, which is just your y. So cosine of theta is x and sine of theta is y. So actually, to make this truly accurate, let's make this a theta. That's why sine squared theta plus cosine squared theta is equal to 1. It's just a consequence of the Pythagorean theorem applied to a triangle whose hypotenuse is equal to 1, which is the unit circle. That's what we've been doing all semester long. Okay. Let's do another proof. Cosine of theta over 1 plus secant of theta. This is equal to 1 minus cosine theta over tangent theta. One minus cosine theta over tangent squared theta. Cosine theta over 1 plus secant theta is equal to 1 minus cosine theta over tangent theta squared. Prove this. Which side would you guys like to start with? You want to start off with the right? Let's start off with the right. Here it is. What do you want to do now? Great suggestion, Robinson. Now what? We can multiply top and bottom by the reciprocal. Now what? Since we're multiplying, I'll just work across here. Since we're multiplying, this is what we get. You only need to get a common denominator if you're adding fractions or subtracting fractions, not multiplying. Multiplying, you multiply numerator times numerator, denominator times denominator. So like 8 over b times c over d is ac over bd. Now what? Pull out a cosine. From here?
No, never mind. It's already out.
So what?
Shouldn't sine squared theta equal 1 minus cosine squared theta?
Yes. Sine squared theta should equal 1 minus cosine squared theta. No, because sine squared theta does not equal 1 minus cosine of theta. That is not true. Why do we pull out a cosine? Like Marcus said.
I thought it was already pulled out. Oh, okay. Never mind. I'm confused. I thought it was already out.
There's already one pulled out, but you could pull it out again. And here's why that might be a good idea. It might allow you to introduce a secant. Let's see where it goes. I'm just following what you guys are saying right now. Does that make sense? So this becomes a cosine cubed theta. This becomes a 1 over cosine of theta minus 1 all over sine squared theta. But notice this becomes cosine cubed theta times secant of theta minus 1 all over sine squared theta. Now what? Now what? So we're at this point right here. We started off here. We want to get cosine of theta over 1 minus secant of theta. Why don't we analyze what we're trying to work towards? This should be cosine of theta all over 1 plus 1 over cosine of theta, right? Okay. But that's also cosine of theta all over cosine of theta plus 1 all over cosine of theta, right? But then when we multiply by reciprocals, this becomes cosine of theta over 1 times cosine of theta over cosine of theta plus 1. But that's cosine squared theta over cosine theta plus 1. So if we can get what we have to be a cosine squared theta divided by cosine theta plus 1, we'll be done. What do you guys suggest to do?
So we have to pull one off of the 3, right? The 3 and the cube cosine,
Say what?
because there's 3, right?
Uh-huh.
And so we have to get 2 on the top and 1 on the bottom.
Yes. Plus a 1.
How do we get rid of the time?
How do we get rid of the sign? This one?
Yeah.
Well, you could try to use this. So let's see here. Why don't we send this through? Notice we get cosine squared theta, and you multiply that times that, minus cosine cubed theta over sine squared theta. Right? And like Maya suggested, is it Maya?
Yeah.
Maya. We could say this is 1 minus cosine squared theta. You wanted to get rid of the sine. Now what?
Replacing 1 minus cosine squared theta.
Hmm?
I'm going off of what's on there to get rid of sine.
Mm-hmm.
So it's gonna be 1 minus cos squared theta.
Yeah.
Sine is equals to that.
Yeah.
You. So those cosines, the cosine twos cancel out, or they negative?
You want to cancel out the cosines? You have to factor out a cosine squared. That's what you would get. If you factor out a cosine squared from the top and the bottom, that's what you would get. And you could cancel, which that would reduce you to, if we now give them a common denominator, you get 1 minus cosine squared theta all over cosine squared theta, right? So then multiplying by reciprocals, you get 1 minus cosine of theta over 1 times cosine squared theta over 1 minus cosine squared theta. Which gives you what? Notice this bottom can be sine squared theta. So then this whole thing becomes tangent squared theta. And then what? Oh, this needs to have a square on it. How did I say that? How did I say that? Well, cosine squared theta over sine squared theta is really cotangent squared theta. But that's 1 over tangent squared theta. So that's why I made it into a 1 over tangent squared theta. Now what? Oh, looks like we started right where we started. We went back to where we started. We didn't prove it yet. We went around in a circle. We started here, we started doing stuff, and then we ended back right here. That's not what we want. What we want is we want to start here and end here. So let's try it again. But at least there's a point in doing this, guys. There's a point in allowing you guys to make suggestions and us to explore them. You see how to do it. If I have this idea, how do I pursue it? You pursue it just like we did just now. It might make you go in a circle. But guess what? That's exactly how you solve these. Sometimes you have to go in a circle. So you guys want to start off with the right-hand side, right? So you got this. We want what's in this yellow circle. Cosine of theta plus 1 secant of theta. We notice that's the same thing as cosine of theta over 1 plus 1 over cosine of theta. Okay? We notice that's the same thing as cosine of theta all over cosine of theta plus 1 all over cosine of theta. We then notice if we multiply by reciprocals, this is cosine of theta over 1 times the reciprocal of the denominator, cosine of theta, times 1 plus cosine of theta. We notice that this gives us cosine squared theta over 1 plus cosine of theta. So this is a neat little thing we can work towards. We can work towards having a cosine squared theta over 1 plus cosine of theta if we start with this. Let's try and get there. You guys initially suggested this. You said, okay, why don't we do that? Because that's what tangent squared theta is. Well, let's multiply by reciprocals to get this. Okay, what does that get us? Well, that's what that gives us, right? So in the numerator, we want that cosine squared theta, and it's there. But we don't want this 1 minus cosine of theta business. In the denominator, we want this 1 plus cosine theta, but we have a sine squared theta. That's not what we want. So far, the only thing that is going the way we want it to go is that we have a cosine squared theta in the numerator. You guys see what I'm saying? You don't see what I'm saying? So this is what we're trying to make it look like. Starting off with this. We substituted what tangent squared theta was, did some rearranging, and this is where we got to. And what I'm saying is the only thing that mirrors our final destination is that we have a cosine squared theta in the numerator, and that's it. The rest of that algebraic expression does not look like this algebraic expression. The only thing they have in common is this cosine squared theta in the numerator. You up to speed? Okay. What can we do now?
Do we need to get the stuff in the parentheses to the bottom? Because then that would help us get the plus one in the tangent.
Yeah, kind of. We want this stuff to go away, and we want this to turn into a 1 plus cosine of theta. But we can't just like replace it willy-nilly. We have to do algebra on it. How do you guys suggest we do that? I like Maya's idea, but I'm going to take it one step further. If you multiply top and bottom by the same thing, you could say that that's just a fancy number 1, right? Why did I pick that one? Why did I pick that fancy number 1? Let's see. We get the cosine squared theta just comes along for the ride. 1 times 1 is 1. 1 times cosine theta is cosine theta. Negative cosine theta times 1 is negative cosine theta. Negative cosine theta times cosine theta is negative cosine squared theta. And this becomes sine squared theta times 1 plus cosine of theta. Notice that these cancel. So we get 1 minus cosine squared theta. Why did I pick this fancy number 1? You will see soon, because notice what is this the same thing as? Yeah. So that means so that's the same thing as sine squared theta. And then we can cancel them. And then we're done. Because we can retrace our steps from here. Back over here. And then back over here. Notice that this is what's here in this box. So I can retrace my steps here. I won't erase the retraced steps. So from here, let's work this way. Let me retrace the steps. If I want to go from here to here, I already know what to do. I multiply this is the same thing as this. And then retracing your steps even further, that's the same thing as this. Retracing your steps further, that's just this. Retracing your steps further, that's just this. And you're done. Let's get more practice, because this stuff, nobody's born knowing how to do this stuff. It takes practice. So the key was to multiply top and bottom by something called the conjugate. You guys know if I have like 3 minus square root of 2 over 5, that I can multiply the top and bottom by the conjugate, right? And it'll make that square root go away, at least in the numerator, for example. It's just an algebraic trick. For example, this becomes 3 times 3, which is 9, plus 3 root 2, minus 3 root 2, minus a 2, all over 5 times this quantity. These middle terms cancel, so you don't get something with a square root, you just get a 7 up here. So this is called multiplication by the conjugate. You get this term and flip it. Reproduce this whole thing, just get this term and flip it, and multiply top and bottom by that quantity. It can allow you to cancel some things out. Notice that multiplying by the conjugate was an essential step for us to prove this identity. So our conjugate was multiplying top and bottom by 1 plus a cosine of theta. Why? Well, we had 1 minus cosine of theta. If you multiply it times this conjugate, what do you get? You get 1 minus a cosine theta plus a cosine theta minus a cosine squared theta. When the middle terms cancel, you get this 1 minus cosine theta. But that allows you to invoke the Pythagorean identity and say that that's a sine squared theta. So if you have a cosine to the first power or a sine to the first power subtracted or added to something, if you multiply it times this conjugate, you could get it into a squared version. And when you get into a squared version, you can use this identity right here, because this is an identity about squares. So it allows you to transform it if it's to the power of 1 to the power of 2. And that allows you to use this tool. Let's do some more examples. Man, you guys think it's hot in here? Man, I'm burning up. It's hot and I'm hungry. Not a good combination. I just want to jump into a swimming pool made out of shrimp and sushi. Okay, more examples. What about secant over sine minus sine over secant? Let's have this equal tangent squared plus cosine squared over tangent. Prove this. Which side would you guys like to start on? Usually there's a side that's easier to start with than the other. So picking a side is kind of important in terms of like getting the proof done in a quick manner. I would suggest starting with the left side, and here's why. You can get them have a common denominator. They don't have a common denominator yet. Maybe when we establish a common denominator, things might kind of work themselves out towards that. right-hand side. I'll reproduce it. Right? So we'll reproduce it. We have to multiply top and bottom here by fancy number 1. What it lacks, the secant of x. And I have to multiply top and bottom here by it. It's fancy number 1. What it lacks, the sine of x. To establish the common denominator. Right? So then it becomes secant squared x minus sine squared x. Everything divided by secant x sine x. Okay, now what? We want to work towards tangent squared x plus cosine squared x over tangent x. Now what? We flip a page and we take a look at our identities that we have at our disposal. We have an identity that relates secant squared to tangent. You guys remember that the secant squared is equal to tangent plus 1? Tangent squared x plus 1 is equal to secant squared x. This is an identity that you can prove. And we have a secant squared. We can replace it with this tangent x plus 1 or tangent, yeah, okay. Why do we want to do that? Well, we want a tangent squared term anyways, don't we? So that's a good way to introduce that tangent squared term in the numerator by replacing it here. So this becomes okay. Now what? I'll give you a hint. What about thinking about it like that? Or this is a plus. What do you see here? Yes. So what can I replace that yellow circle thing with? Cosine what? Yes. Why would we want to do that? Marcus, why would we want to do that?
Because of the cosine squared. We have to find cosine squared.
Yeah. It's how we want it. We have a tangent squared plus cosine squared. The numerator looks good. The denominator, not so much yet. Right? The numerator is looking good. Now we got to tidy up that denominator. Any suggestions?
Substitute the secant for 1 over cosine.
That's a great idea, Robinson. Now what? This is a plus, by the way. It looks kind of bad. Now what?
One over cosine is cancel.
Say what?
I'll leave it alone.
Oh. Oh.
If we want tangent at the bottom, so we use sine of x over cosine.
Say what?
We want tangent at the bottom.
You want tangent on the bottom?
Yes.
Can you just want things into existence? No.
But since we have sine and cosine, can we do tangent by definition? Sine of x over cosine of x. Can we just
What do we do with the 1? Dude, earlier I said when you multiply fractions, the tops multiply and the bottoms multiply. So 1 over cosine of x times sine of x over 1 is this. Oh, that's tangent? That's a tangent? No, yeah, it is. Who said, oh, who made that noise? Who made that noise? Was it you? Did you have a light bulb moment? That means if we took a positron emission tomography scan of your brain right now, that you have activation in your left temporal region. Now what? You're done? That's it? Okay, you guys are right. You shouldn't overuse that technique. You should like use it a little bit and then like let the students forget that you use it and then use it again. You guys are adaptable. You catch on quick. I'm gonna have to get more clever if I'm gonna mess with you. Let's do another one. Let's show this one. Show that one. Which side do you guys want to start off with? The left side has the most stuff, but doesn't that make it more complicated and annoying to deal with? Yeah, it's just 1 over cosine.
It makes more sense to do the side the most stuff,
Why is that?
because I already know what secant is.
Okay. So you have more stuff to work with? Is that what you're saying? Oh. All right, Maya, you've convinced me. I'll rewrite the left-hand side. Now what?
Where that x just come outside? Since sine, but sine is an odd function, would it be negative sine of x?
Huh?
No,
No, no. Just say it again. You say it again.
isn't sine and odd function, so the x will come out in front of the negative of the sign.
The negative would come out of the x, not the x would come out of the negative. Here's Robinson's suggestion. This is a negative, by the way.
I have a quick question.
Yes, ma'am.
Why didn't you just divide? I mean, take away the minus x on the top and bottom, since they can go divide each other.
Because you can't do that. You can only cancel if they're being multiplied or divided. You can't cancel. You can't cancel if this is being added to. This doesn't work.
Can't we just make the double negative a plus?
What?
Because it cancels out.
Negative times a negative is a positive?
Yeah.
Yeah, you're right. So, to honor Maya's suggestion, we'll rewrite it like so. I'm overusing it. The incredulous intonation I'm overusing. I was born really socially awkward, so I have to kind of like read books on how to act normally in real life. I read that intonations in your voice can imply things without saying them. So I gotta make sure I don't overuse it. Now what? We're here. Now what?
Is that negative x connected to the cosine?
Uh-huh.
Can we go back to the two processes together?
No.
Because one of the x.
You said sine was an odd function, right? What is cosine?
Even.
What does that mean I could do with this negative in here? Make it go away. Now what? Still doesn't look like a secant. Huh?
Don't you have cosine, sine? No, it's substitute sine, cosine, cosine.
Say what? Say what?
Can you substitute cosine, sine for, because tangent for t plus 1 is equal to secant.
But cosine times sine isn't secant. 1 over cosine is secant. This is 1 over cosine.
You have to multiply by the cosine.
Say what?
Multiply by cosine.
Multiply what by cosine?
The numerator.
No.
Well, not the numerator.
This term, let's look at this term. It's got a cosine in it. This term, it's got a sine in it, but it also has a cosine in it.
You add them together.
No, they're already being added together. Hence this plus. You gotta have fun with this stuff. It's like a puzzle.
So you can't make it cosine 2x or something like that?
No, you can't. It's a good question, but you can't.
Are we stuck?
Huh?
Are we stuck?
Yeah, you guys are stuck, but I'm not stuck. Because I know I can factor out a cosine from the denominator to get this. Notice I was giving you a hint. This has a cosine in it. This has a cosine in it. Let's pull it out. Why should you pull it out? Because the what?
Is it fancy one?
Wait,
Like the one over there?
oh, it's a fancy one. Yeah, I see what you're saying now. Yeah, this is a fancy one. Now you can cancel. Why can you cancel now when you couldn't before? Well, it's this whole thing being divided by this thing times this thing. So it really is division. Division and multiplication. So we can cancel these terms out and we get 1 over cosine. Which is what? Yeah. So we're done. Make sense? This stuff is going to take practice. You gotta practice this stuff a lot. This stuff is on some of my favorite stuff in math. Proofs. Let's do another example. Cosine to the 4th x minus sine to the 4th x all over cosine squared x is equal to 2 minus secant x squared x. Let's prove this one. Oh, there's 4 fourth powers, huh? Is that worrying you, Maya? No? Good. My students don't get scared off by 4th powers. Is your arm going numb? It's a good thing it's not your left arm because that's a sign of myocardial infarction. It's a fancy term for a heart attack. You're not getting a heart attack, are you?
No.
Okay. Which side would you guys like to start off? The left? The left?
Yeah.
Why? That side is too easy. Let's start off with a hard one. Well, now what? We're already on our way to solving it. We just rewrote it. Now what? I noticed that we're working towards this right here, right? But this is equal to 2 minus 1 over cosine squared x, right? But if we multiply top and bottom here by fancy number 1, which is cosine squared x, we get 2 cosine squared x minus 1 all over cosine squared x. So if we can get that out of this, we'd be good.
What is,
We have to pull out a cosine? Or pull out
Just one?
two?
Just pull out 2? Where?
The top.
The top? All right. That's what you get when you do that. Now what? These cancel, right? So this is what we get.
you should just use a sine to the fourth power of x, so cosine is not
Her tangent, well, you could write this as, this doesn't mean it's helpful. I'm not saying this is helpful, but you could write this as this. If that's what you were asking.
Can we turn that tangent into sine over cosine?
Sure. What now? We have 4 minutes left. Say what? Cosines do not cancel out. All right, you guys keep wondering how can you cancel something out? You can only cancel out multiplication with division and division with multiplication. Addition can get canceled out by subtraction. So look, if I have x times y plus 3 over x plus y, I can't just cancel out these x's. You're canceling out multiplication with addition, and that's not possible. Now, what you could do is factor out of x. Now you could cancel. But you can't just cancel right away. You could do it here because now it's multiplication being undone by division. So why don't we retrace our steps back to this point right here? Why don't we, instead of take out 2 of them, take out 4 of them? Right? Does that make sense? Maybe we could cancel out 2 here and 2 here. Now what? Now what? Was that not an identity that we used? That secant squared is tangent squared plus 1. Is this not an identity that we've used before? Right? So solve for tangent squared. Here's another re-expression of that. But we have a tangent to the 4th, don't we? We have a tangent to the 4th in what we're dealing with. We only have a tangent squared here. So you could square both sides of this equation, actually, and get a tangent squared here. Or a tangent to the 4th. You guys see that? So you can replace that with okay, this reduces to cosine squared x times secant to the 4th x minus 2 secant squared x plus 1. Okay. Then you notice that this is really 1 over cosine to the 4th x. And when you send this cosine through, you get that this equals 1 over cosine squared x minus 2 cosine squared x times 1 over cosine squared x plus cosine squared x. When you send that term through. Notice that this cancels out to just give me a negative 2. And this is a secant squared. So this is negative 2 plus a secant squared x plus a cosine squared x. Time is up, but you could move on through this calculation and you eventually will end up with this expression. Okay?